So the first basic one we'll start with is the constant function. And as you see, the constant function here is, its slope is 0. So that should give you that the derivative of the constant function is 0. So that's the first one we need to know. And saying that, if we go to like homework, so for this differentiate the function, there is no x is the variable. That's not, it's not a power formula as far as the function, but it's just a constant, right? So the derivative of this one, it's going to be 0 because 2 power 60 is a constant. All right. So we can't mix between the power rule that we will learn later on and these constants. The power function, which is the next one, let's say f of x, the basic one, y equal x, and of course x to n can be any other positive number there. If you try the formula that we did in the past, you'll find these things, 2x for the x square, derivative of x cubed 3x squared, and of course you can prove it by, let's say, taking x to the 4th. But now we're going to adopt these formulas, so we won't have to go through this process again. And we've done this process multiple times. So if you want to investigate, you can. You'll take the x to the 4th, x plus h, and f of x and h, and you just break it apart. And when you simplify, you cancel the h. You'll find that derivative to be 4x to the 3rd, which gives you that pattern of the 4 comes to the front, and this minus 1 becomes the exponent. And then we'll see little other details later on. So the power rule is a new formula that will take over all this process, right? It will take over. And if we have a function that is in which we can apply this power rule, it's just going to be n times x times power n minus 1. And these are some examples. X to the 6th, the first derivative is 6x to the 5th. So if I want the second derivative, then it will be 6 times, then now 5x to 5 minus 1, which is 4, right? And so forth. So, and you can see these examples, and they're the same thing. So the power rule in general, it's this one here. And there are some other details we'll talk about later. So what is the new derivatives from the old? When new functions are formed from old functions by addition, subtraction, or multiplication by a constant, their derivatives can be calculated in terms of derivatives of the old functions, right? So if we know the old functions and now you have a combination, then you can break them apart or apply the rule to still use the rules of the old functions. So if you have a constant, then you can just put that constant outside. Derivative doesn't apply to it, and you just do the derivative of f of x with respect to that x. So example here, differentiate, let's say f of x is 3x to the 4th. Like I did in that example, 3 weights, right? And you do the derivative of f of x, which is 12x cubed. And you see, so there is no more quotient formula and taking the limit. -1, this is -1, we do a similar way. And so for x, what is the derivative of x? You do 1 it's going to be 1, which is this one, times x1 minus 1, which is 1, x power 0, which is 1, right? So that's, keep in mind that. So for the constant, it's 0. For x, it's 1. Those are common ones. The sum rule. The derivative of the sum is the derivatives, the sum of their derivatives, right? And so forth if there is more than one. The difference of the derivative is the difference of their derivatives. That's not a problem there. Exponential function here, there is some explanation to it, but what you need to know, of course, before I go into explanation, not to confuse, is really what you need to know. In general, everybody needs to know this idea of the E number, where it came from, and it's, you have it in your calculator. You can try it and see, like E power 1. It comes up to like 271,828 and so forth. And where this number came from is, and there is this limit here. E is the number such that if you take this limit, it equals to 1. But let's show first what you need to know before I talk about that, and it gets confusing. So in this section, for exponential function, you need to know that the derivative of the EX, right, is the same. That's one. So here, this explanation is just to kind of try to justify what happens, or where it came from, which means, so we start again with the idea of the slope or difference quotient. We take the limit, which is definition of the derivative, then we separate these two, and we're able to separate this one because here you're taking the limit in terms of h. This does not have h, so it's just like a number in this case. And you know, it gets checked. This one here, it's like b0 over h. So this thing kind of acknowledge that it's f prime of 0. But for anyone who reads this, it may not be clear right away that, okay, you're saying, you know, this thing here, and somehow you're saying that's f prime of 0. How do we know that? So kind of math thing, they investigate and they find out that this thing is, of course, so it's like f prime of 0. And so this formula here becomes this number 4. The derivative is f prime of 0 times bx. Then they do some investigation with computations. Let's say b equal 2. You know, you see the values that we did in the past. Similarly, what happens, you get this thing to be 0.6932. And for the, if it's 3, what do you get? You get this one for the lowest one. So this it's not something you need to worry about, but if somebody is interested how this came about, that's now they, you know, this is the process, which is similar to what's in the textbook. Then you know, then the new formulas come for the derivative of these. But now to simplify things and to make f prime of 0 equal 1, there must be a number between, and I'll show you a chart. There must be a number between this graph, and they find out that it's EX. So the whole thing here, the whole story here is to get to this graph, which means at f prime of 0 at here, this slope is 1. F prime of 0, slope is 1. And when you get to this here, you'll find that the slope is EX. So as I mentioned, if you're interested, you can read more about it in the book, but there is a long explanation to it and how the investigation is done and how we're interested in simplifying. So we make the assumption that to have this, but to make the story shorter, this is the interesting part. So example, if we have this function, find the first derivative and the second derivative. So if you apply it, you see now you have a difference. So you can apply the difference formula, which means the derivative of ex, subtract the derivative of x. This one is the same, and this one is 1. Then we do that again for the second one. And the derivative of 1 is 0, which is because it's a constant, and you get ex. And of course, in 2.8, we investigate the curves, and you can see kind of the relationship between f and, when you have this horizontal here, the derivative is 0, so it crosses. Here the derivative or the slope is decreasing, so there is a decrease, which means it's negative, so it's below the x-axis, right? And here it's increasing, which is positive, so the derivative is going to be above the x-axis. Okay, so some examples from the homework, and I need to get the numbers of them. Okay, so let's look at the question. So we are in 3.1. This one is question 2. The other one I did is question 1. There is a product rule we didn't talk yet about. So when you can apply it, but in this case, let's say we don't know that one yet, and we want to apply the power rule. In that case, this is going to be 3x squared plus 5x minus 12x minus 20. So 3x squared minus 7x minus 20. So that's h of x. Okay. And if we want to find that derivative, now we're going to use this one. It's going to be a difference of each one. So the derivative of this, subtract the derivative of next one, subtract the derivative of this one, the difference rule, right? But the derivative of this one, you have a number. So let's do the derivative of this one, that's a c, the number, so you keep the number. Now you do the power rule on this one, 2x2 minus 1, which is 6x. Then we get to negative 7x. C is negative 7. The derivative of x is just 1. And negative 20, it's a constant. The derivative of constant is 0. So it's just 6x minus a 7. And this one is number 5. Just to show that, if you have something like this, you're always going to try to get that power rule in place. So you apply it. So this also, that's what it means for this exponent. You see, in the past, we don't like negative exponents. We switch a positive. But now you see that's not the goal. The goal is to get the power rule form so we can use it. So we switch it back from the positive to negative. Then we're going to say the c is negative 11 times. Now we need to do the derivative of this thing, right, with respect to s. The variable is s. So the power rule says it's negative 6 times s, whatever it is, minus 1, right? So 66 s minus 7. And it'll be 66 over S7. Next, it's number 7. So it's not bad. It just as we go, we're going to have multiple rules, and you know, you just need to understand which one applies to what, and it should be okay. Differentiate the function. So here, what we do is we're going to, you see, separate this as 4 over, so there is a sum, which means we need for these derivative, we're going to need to do the sum of their derivatives, right? Let's make this thing one big one. So the derivative of each part, and they're added. Then if you want to apply the rules, so 6 goes out, just to show details, and we skip them later. So the 4 again is same for d over dx of, this is 4 times 1, so 1 over this thing. And we know that this thing is x to 1/3, right? So 6, and it is at the bottom, right? So if you, it's going to be negative 1/3 to go up. So it is at the bottom. So if you do this, then it becomes this. So now for the derivative, it's going to be a 6 ex is the same, plus a 4. This one, the power rule will say 4 times negative 1/3 times x minus 1. Minus 1 means over 1 times 3 times 3. So it's 6 ex minus 4/3 x minus 4/3. I think this is okay. You can switch it back if you want to, but it should be okay for this one. So let's now apply, now we'll connect, because once we know this derivative and the slope of the tangent, we can also figure out the normal line, which is that perpendicular line that you will need for future subjects. So let's do that. So we'll start with the tangent, A. We know that's for the tangent, it's just the derivative, which is d over dx of these two. And as you see there, we can apply the rules to them. And that's going to give us the power rule again. And the exponent again is the same. We are interested at 0.06. So y prime at 0, because that's x. And 4 times 0 to the 3rd plus 6e times 0, which is 4 times 0, right? Plus 6, which is 6. And this one should be number 11. And we go back to find the tangent. Now it became a regular question, right? We do the f prime at 0. of x minus x1, and this is a 6 and this is a 0, and we found that this is a 6 as well, right? So y minus 6 equals 6 times x minus 0. So y equals 6x plus 6. So this is the equation of the tangent. To find the normal, we know that the normal at that point is that perpendicular line, which means its slope is going to be the opposite reciprocal of the one we found. So it's going to be negative 1/6. So applying the same formula again at the same point, just now the slope of it is negative 1/6. And y equal negative 1/6 x plus 6. And that's for the normal. So you see the work kind of got simplified a little bit. Let's look at, so of course you can pause the video and check back and stuff, but you see the question is about this point, the tangent line and the normal line to the curve at this given point. And of course this came from the normal line is the perpendicular line at that point. So if you have a kind of, this is a tangent, then the normal is going to be, let's say, something like this. So what is this one? I think number 13. The equation of a motion of a particle is this, where s is in meters and t is in seconds. Assume that t is greater than or equal to 0. Find the velocity and acceleration as functions of t. So when we talked about these parts, we talked about that the velocity is going to be that first derivative, and acceleration is going to be the second one. So for A, the velocity here is going to be this first derivative, which you'll do the power rule, and t is just like x. So remember, the variable for which you differentiate is the one you're going to be using, and we will see this later on a little more, and it makes a difference. So it doesn't mean x, it means whatever variable we're differentiating to. So for here it should be ds to dt. So that's what we're doing, ds to dt to this, right? And then when you split it, it becomes right. So you see this is 1 and this is 3t squared. So that's the velocity. Now the acceleration is that second derivative. So this one is s prime. And the acceleration is going to be 6, which is 3 times 2, 6t. And the derivative of 3 is 0. So that's the second derivative there. Find the acceleration after 6 seconds, which means this second one, 36. Now find the acceleration when the velocity is 0. So what does this mean? Let's look at the velocity. The velocity is 3t squared minus 3 when this is 0, which means t squared at 3 divided by 3, 1. So t is the square root of 1, but t is greater than or equal 0, which means 1. So when the velocity is 0, it's at t equal 1 second. Now we can use that for the acceleration. 6 times 1 equals 6. All right. Okay, so please try, and if you have questions, let me know. Thank you.